um, that's kind of my background and like where I'm coming from for the in my interest in cloud computing. I have to say, like, I've been extremely impressed with this cross-disciplinary workshop in the COSPAR meeting. There's an incredible range of cloud-based and machine learning-based approaches and tools. It's quite amazing, and it's been this session in particular, or today's sessions in particular, I think have focused a little bit more on the human aspect behind these like clouds are very technical, as we all know, but like this session has really sort of promoted the more human aspect, and how do we get more people involved so that ultimately the science is better. So that's kind of where I'd sort of like to maybe start off, sort of thinking about that. I don't know, Mark. Should we just move into the panel discussion, or?
Well, I have specific questions actually for Chris and Fernando, actually.
Oh, sure. Yes. Yeah. So do I. We could do that first. Yeah.
Maybe I'll ask Chris first. So I lead a team of scientists, and recently for some project we have some grants from a cloud vendor. I can just say it's Google Cloud for a certain project. Okay. But if we wanted to use your services, how does it work? Do you work with all cloud vendors?
Can you hear me?
Yes.
Cool. Yeah, so we're still working out like exactly what the kind of service model is going to be. But the short answer is, yeah, that's the goal. I mean, what we want to do is to be able to say, if you have cloud credits on provider of your choice, then you can just sort of give us the keys to a Kubernetes cluster, and we'll be able to just manage some kind of customized Jupyter Hub infrastructure on there. So it's kind of like, imagine you would have an engineer in your own organization that you just rely on to deploy the infrastructure. It's just that this person happens to be inside of this nonprofit organization rather than embedded in your own institution.
Okay, and do you conceive that it might be an administrator that would be in my organization working with an administrator from 2I2C together?
So in my experience, and this is more just my experience working on hubs like at Berkeley and across the other communities, there are sort of a few important roles that you need to have for these kind of shared interactive environments. One of them is like an engineer, someone who just understands Kubernetes and understands cloud deployments and can keep them running and upgrading and things like that. And then you need someone on the sort of the domain side or the user side. And this is usually either like a professor or a leader of a group or like an instructor of a class. And they are kind of like advocates for the infrastructure on behalf of the users. And they are kind of like, usually they're more like power users. They understand a bit more the combination of both the domain and the technology. And they can help guide like infrastructure decisions that are made for whatever the use case is. And so usually in these hubs, in my mind, like the engineer works in 2I2C, the sort of advocate or the domain person works on the whatever other organization we're working with. And part of that is because like we want, 2I2C's core competency should be in like running and deploying and developing really good infrastructure for research and education, but we don't want to have like a really specific domain focus. And so really we want to sort of like force multiply people who are in other fields or in other institutions. So that's kind of where I see the like organizational connection point is between those two people.
Cool, thanks. Okay, I can ask maybe Fernando a question too. Well, first a short question. when you showed the demo of GDL, I think I missed it. What is GDL?
GDL is the package that I made, which is available on GitHub to download the NASA satellite imagery easily with one line in the command line with the inputs. So it's just a tool to download imagery.
Okay. For a few moments, I thought you had to learn this GNU version of IDL, which would have been a terrible project to subject students to. I would like to comment that I'm very impressed by your talk and also the talks in the ML for space science sessions from the other students. So we at our lab we have high school interns. We've been having high school interns every year for like 2 decades, except last year. And sometimes the interns are really good. And I sent an intern to a meeting once, and he gave a poster presentation, and then a NASA person wanted to hire him on the spot. So it's sort of that level. And certainly we have a need to like make a TensorFlow version of the SDO-ML data set. So we should definitely talk about it later if that's interesting for you folks. That's all I wanted to say. Jack, back to you.
Well, I completely agree, Mark. I think so. The work that Fernando and I forget the name of your colleague. I apologize. So I mean, you're doing a lot of the work that a lot of scientists know they should do, but don't really want to do. And so, like, it's an incredible service, right? Like most scientists just want to get on and do their science, right? But to make something ready for TensorFlow, so like as you said, like, you know, it's a 2-liner to do something. I mean, that's like that approach is, yeah. If we can generalize that, that would be incredibly powerful. It would save a lot of scientists time, I think, and probably, and you know, lead to greater adoption of machine learning approaches, I'm sure. So, yeah.
Can I just add something real quick? So what you just said reminded me a lot of what I think is one of the most impactful parts of the Pangeo project. And most of the stuff that I talked about in 2I2C is focused on like kind of like hub cloud infrastructure stuff. But I think there's like a whole other story that I still don't know if it's in scope for 2I2C or not, around data engineering, which is like a ton of work, but it's work that usually requires more domain knowledge than just like a kind of generic like cloud DevOps-y sort of person. But it's really important in order to actually gain the benefit of all of this infrastructure that's starting to be runnable on the cloud. I know like a lot of the legacy of Pangeo, a lot of the work that they've done is in standards for like cloud native data formats and contributions to open source packages in the cloud native data format space. So like there's a package called ZAR that runs on object file storage, and that's like everything that Pangeo uses builds on top of ZAR. But whether it's ZAR or some other, you know, machine learning optimized format, it's going to be a lot of work to build not only the tools but also the practices around converting data that may have been collected in a legacy format or in a format where you didn't have a lot of control over it. And you need to figure out like what are those pipelines to get it into either like a cloud native state or in like a, you know, a state that one of the machine learning frameworks knows how to like quickly churn through. I feel like that's kind of like in my mind an oncoming really huge challenge in the field to fix, both with improvements in infrastructure and tools, but also just around like practices and education and skill sharing and things like that.
Yeah, it does. You know, I have questions about Pangeo. So does anyone know how long has Pangeo been around?
I want to say it's about 3 to 5 years now, something like that. It's quite recent.
Right.
Is there like an underlying question to that question, or?
Well, so like, you know, if you were to, like, what I'm thinking is, if you were to stand up like similar efforts in different space science disciplines, you know, will it take 3 to 5 years every time because of the domain knowledge? You know, if that's, I guess, because you've done it once, then that helps, but still, like, I mean, I think you're right that the main issue is taking the domain science and translating it into a cloud context. So, I mean, we just haven't, like, a lot of our data formats and data systems are not built for that. And so, like, that is a major barrier going forward. But if it's going to take 5 years, if it's going to take 10 people 5 years, that's a big ask in most space science disciplines, I would say.
I think the bottleneck is not in developing something that is like Pangeo. If you're talking about like a heliophysics, it's not developing an ecosystem, a brand new ecosystem that could be used for heliophysics that Pangeo uses. It's actually the whole stack can be used for heliophysics, and Will Barnes, one of the people we know, he's been using Dask and all that stuff to do some heliophysics analysis at scale. The biggest bottleneck is having enough of those people around to be able to apply these new stacks. And I think one of the questions that you were telling me you wanted to pose was about how do we train the cloud natives, a generation of cloud natives to be able to do all these things. And I don't know from all the people online what your opinions are about that.
I can give it a general shot. So, you know, good software is about building good and clear abstractions so that it's usable at more places at the end of the day. So for example, if you're building it for one use case, eventually you can abstract away, okay, where is the data coming from? Where is the training happening? So that the training could be for a different domain, which you didn't intend to at the start, but, you know, a subject matter expert in that domain can come and, you know, change that. One of the examples, for example, in the SpaceML examples that we are giving, Fernando sits like at the starting of the pipeline in building this, but literally every tool we built is command line based because we don't expect our users to know deep learning. But with one line of command, with one line of command, you know, they don't need to run Python programming or deep learning. They can train a self-supervised network. They can train an image similarity thing. They can turn on and, you know, run a cloud search platform. But as we're doing that, turns out we have a similar use case with the Hubble Space Telescope data, where they want to find examples which are looking similar, so that what areas need to be, you know, zoomed into should be seen by more people. And that's where, like, you know, these abstractions really help, because we never had, because we started with good design patterns. A new user could come in and not in the machine learning domain, and in a couple of days they're already training their own things because everything was in a very easy available way. I think the point being, you know how we say we stand on the shoulders of giants who have done the work, and then bringing it into a new domain takes a much lesser amount of time. Now, the important thing is that once you go in that domain, you need to be the PR person also. You need to go around and talk about, like, how cool is this, I'm using this tool, and be the promoter of it. And that's how, like, things spread, essentially. So I think we need both people who are users, but also the evangelists at the same time, especially in areas which are slightly more niche right now.
So Chris, do you have like a evangelist package that helps the domain experts sell your solution to the organization so that they get the support to implement their vision?
I mean, one day. Right now we don't have any money, so no, not right now. Neither does Jupyter itself. But I think that in my experience, that person is often an individual who's embedded inside of a community already, who just cares a lot about, practices and tools and infrastructure, and they intentionally or not become advocates for a particular set of workflows. I mean, and in many ways, Pangeo is a good example, right? Like Pangeo is the leaders of Pangeo, they're not infrastructure people, they're domain scientists. And they had really large data sets that they wanted to run on the cloud, or that they wanted to access in the cloud. And so they started doing infrastructure work that allowed them to get closer to that. And, after a year or two, they found themselves running a ton of infrastructure. And, even though they don't think of it as their job. And so in some ways, I think that one of the things we need are organizations, and this is sort of what led to the creation of 2I2C. It's like they don't want to have to spend their time worrying about like debugging a Kubernetes networking error on their hubs, and they were increasingly spending their time doing that. So that they can spend more of their time like teaching and training and advocating and focusing on the more kind of like science specific pieces of these workflows. So I think that we can get a lot out of scientists that care about this kind of stuff and have them advocate on the behalf of these open source tools and things like that. If we can find ways to like empower them and allow them to, not have to spend their time worrying about infrastructure problems that they don't want to have to worry about, whether that's with an API that's like really nicely designed, or like a Python library, or DevOps infrastructure, or whatever. I think that finding ways to empower people that like they have a lot to give their communities, but they're for lack of a better word, wasting a lot of time dealing with like low level infrastructure kinds of things. Like find ways to let them not have to worry about the infrastructure, so that they can become your like power users and advocates.
Are you going to say something? No. I think that's the evangelist. Like I took some notes there. The evangelist role is a really good one. So perhaps that's something that at least I know in my organization, there's a lot of realization that this is a good idea, but like the kind of evangelist going forward, that role I think we need more than one. I think we need a couple of them, and that can really push things in the areas where like ultimately funding can come from. So I also liked the comment on good design patterns as sort of a way to sort of ease the training of going forward. If we have those, then like a lot of the difficult thinking, right, on the problems have been solved to start off with. So I like that kind of idea as well, going forward. But yeah, as Mark said, that there aren't that many people out there, and like should we be starting maybe high school is the place to start, and then from there we can it would just be people who are cloud native. They wouldn't think of doing anything locally on their desktop. So,
but I think that's worth pointing to like changes in the libraries and the infrastructure that starts to design with like the cloud in mind. And by that, I don't mean that they're designing like things that just work on the cloud. I mean, there are like, there are APIs, or there are like Python libraries. Dask is one of them that basically behaves the exact same way, regardless of whether you're running it like on your own laptop or if you're running it in the cloud. And I think that that's been like one of the kind of awkward transition points over the last 6 to 8 years for scientists, is when they had to transition from this will fit on my laptop workflow to this will require like sophisticated hardware workflow. And it's like, okay, suddenly I have to like relearn my entire tool chain in order to get it to work on like a high performance computing center or something like that. And I think that the way that a lot of modern like Python libraries, for example, are designed is with an extensibility in mind, so that the API that you're using as a human remains the same, even though under the hood, there's like quite a different amount of machinery that's being like requested and used for the actual computation. And I hope that we'll continue to see like more movement in that direction. You know, as was mentioned, like there's an art to designing those APIs in a way that is like sustainable over time and fits all of these different use cases. But I think that we're in like a way better place now than we were, you know, 5 or 6 years ago.
Yeah, I agree. So like 10 years ago, started doing some CUDA and OpenCL programming. And that was really fun for me. It was also very painful at the same time, but it's fun because you get the speed ups and it feels great. But then I can't really share that with my colleagues in the sense that find people who want to develop those codes with me because they're just not into doing that stuff. But it's become much more easy to get the GPU speed up gains in the past few years, in the sense that PyTorch and TensorFlow in some ways looks like NumPy, and CuPy starts to be so integrated that I used to, like even 1 or 2 years ago, you had some case statements to check whether it's a CuPy array or NumPy array, but now NumPy can recognize it and call the appropriate like a Fourier transform routines from CuPy. So it's become much easier.
Hmm.
On the engineering side, we've also noticed, like, you know, to Chris's point, that Docker has been especially helpful in replicating whatever we build locally, but also making it scalable to the cloud. So suddenly you can have like 10 different machines that are able to perform the exact same thing, and you don't have to do anything different in how you set up your environment.
I wanted to mention the fact that just for impact, everybody know. So Meher wrote a book which actually features my binder because we had to show how people would replicate things. So thanks for, you know, I mean, as if Jupyter wasn't enough of an impact, I think I'm just excited to be in a session where the things that people are showing is the stuff we use on a daily basis. So it's just amazing.
So maybe to that point, thank you for the thanks. I appreciate it. Maybe to that point, I think this is also where it's really important to have like shared community projects that you know, users and stakeholders from a lot of different domains use and contribute to. And so, you know, to Jack's point, this is a huge challenge historically has been that, like, you know, each group, whether it's a domain or like a mission within NASA or a research group within an organization, they'll work in their own little silos. And especially the ones that have sizable enough budgets, they do end up building an infrastructure stack that like approximates the things that we're talking about. But it's like a fully bespoke thing that only works for them and doesn't really easily port to everyone else. But to me, the coolest thing about Pangeo, and this is probably not a great way to like sell the project, but the coolest thing to me about Pangeo is that it was completely unexceptional in the technology that it used, right? It almost everything that Pangeo did from an infrastructure standpoint happened via upstreaming contributions to pre-existing other open source projects. And those projects are, you know, by and large, completely domain agnostic, completely infrastructure agnostic. They're just, you know, it's like NumPy and Jupyter and Czar and Dask, you know. And I think that model means that the work that they do will benefit a much broader community of people, both within the geosciences and in just the, you know, the broader scientific community at large. And I think that in my mind, sustainability for these kinds of projects and reducing the amount of time that it takes to like bring new fields into the cloud and things like that will require replicating that model so that we can effectively pool all of our resources towards development. And then benefit from all of those resources that everybody else is putting into it. So open source, yeah.
No, I like what you said about stakeholders having different, like making sure that your discipline is like feels like they're contributing, right? That like this is for them, and get the buy-in, right, from the from your community. So yeah, having a lot of different stakeholders, I think, is a good. Um, I'm like inevitably, I'm just thinking about my own domain that like some of our open source efforts, I think, are still how to put this. Like we're trying to expand to broaden that scope of stakeholders, and I think that like when we get there, then like you have a kind of snowball effect, right? That once you get there and you have a lot of people on board from, there's lots of different people singing the same tune. Then I think that's much more powerful going forward. Okay, good.
So I have a specific question to Xin-Fang and maybe others. So I think Xin-Fang earlier said that for the Rubin Observatory, the data will be stored as FITS files. In the FITS format, that's the traditional astronomy data format. And I honestly haven't investigated whether it's the most appropriate format for parallel loading and for the cloud. So I don't know whether, if you're still there, you can comment on whether that was an issue that was actively discussed during the design process for the Rubin Observatory data pipeline. Yeah, you're here.
Yeah, I'm still here. So our software, the framework design actually allows us to be able to just store the files in a different format. So in the future, if we could, in the future, if you want to say store this in a different format, we should be able to expand that in our software and then do so. I guess there's also the question of resources and whether we will have the time to do that before in terms of the priority of our project.
So the baseline is FITS files.
Yeah, so right now we use FITS file. Right now that might be the only implementation of how we store the image files. But the software framework allows us to be able to implement some different backend in the future.
Okay.
But say, for example, for the catalogs, we now will try to store them in Parquet files. Then that will connect with many other tools many have talked about. Then that also allows the astronomers to be able to use those tools with those Parquet files. So I guess that's probably the nice trend.
Okay, that's interesting. I asked this because I'm sort of scared that our project, and maybe Jack is even more scared, is supposed to deliver, I don't know, by that time 10 or 20 petabytes of FITS files to Jack, and I don't know whether that's the actual file format that you want.
When are you going to give me these files?
I thought Stanford is already starting to give you some.
Yeah. It's an interesting. So I have been I have been worried about the particular file formats given applications. So like in solar physics, with a discipline that Mark and I work in, then as I said at the start, the sort of previous way of working of like downloading a series, a small number of FITS files onto your local machine, that worked fine for years, but it doesn't work that well it doesn't work at all for like a 20 petabyte archive. You can't get a decent chunk of that out. And so I can, like, just speaking for myself, I can see that like the issue of like how we store that much data and actually make it useful on a cloud system is something that we're going to have to approach. So that's why, like, going back to Pangeo again, like, it was interesting to see the use of the ZAR format. That would have to be explored, I think, for FITS for files which are currently in FITS format. So yeah, there's some work to do. So, which is part of what Chris was saying about this barrier of like, you have the data and then you have a cloud, but they're not necessarily the data. And it's not just a matter of putting the data onto your cloud system. There's some other things you have to do to actually make it useful.
I just wanted to give a shout to a project that I think is pretty interesting. I'm not super involved with it, at least right now, but it's an offshoot from the Pangeo project that they call the Pangeo Forge. And I think that their goal is to try and provide infrastructure to sort of like hold the hands of researchers who wants to do data conversions from something into a more cloud native format. And they're playing around with that challenge in general, right? Like there's just some things that you're going to have to know about the format and you know, your target format and everything like that. But once you know what those operations are, then there's no reason that you shouldn't be able to like automate the process of converting and publishing and things like that. And so I think that Pangeo Forge is like playing around with this idea of building infrastructure explicitly for that, like, extraction, transformation, loading pipeline to see whether you can remove that, you know, again, like remove the human toil that's associated with just doing the same thing over and over again, and maybe make it easier to not be like completely beholden to whatever format the data happens to be collected in and that kind of thing. So it's a very, very young project, but I'm pretty interested in seeing where it goes.
Okay, yeah, thank you for that. So it's, yeah, there's, yeah, again, in solar physics, there's definitely, we need to be able to support our older workflows, but like we really want to support what the community is asking for, which is, you know, I want to work on a 20 petabyte data set to do science that I couldn't do before, your granddad couldn't do. So that's kind of the future. So what was the data volume for the Rubin Observatory again? It was 10 terabytes a day, is that right?
Around 20 terabyte per day.
Okay.
And
are you, do you know the Daniel K. Inouye Solar Telescope? That has similar data volumes. So have you had any discussion with them at all, or any overlap?
I myself haven't had a chance to work with them. There might be, but I just don't know.
Okay, okay, yeah, that's fine. Okay, well, there was, yeah, I had another question. So for everyone here, let's say somebody gave you as many resources as you need for your project. What are you doing? What are you doing with those new resources? Like, money's no object. You can find all the people you want. What are you doing? What's this magic future that you're in?
I can start because I have more stuff to do than we have.
Please.
But one thing I'm actually currently doing is training a Formula One style car for racing without going to the racetrack, because it's like a $2 million car. You don't want to crash it before running it. So it's basically, we built a video game simulator where the car tries to learn by crashing, but then it tries to, whatever the best AI we have every day, we try to beat itself with it. So the best AI car is trying to beat the best AI car of yesterday, and they compete and they learn from all their mistakes. So I think that's one cool thing. The other thing, which probably is maybe better for this discussion here, which is like, you always don't need enough money. I mean, I'm not saying no to money, but you always don't need enough money to find an optimal way of achieving the same result, because things actually start plateauing. So one of the problems that we are looking with was with the NASA impact team, whose data set is, I think, already about 40 petabytes right now, and they want to search those 40 petabytes. And literally one forward pass on a neural network over the data is, we calculated it's like $30,000 of cloud bill, like just one pass, and this is not even doing anything. And we had to do like 10 passes over it. And we found that we found ways of sampling the data in such a way that it represents the exact core balanced data set of like the petabytes, so that if we wanted to do something now, we could achieve the exact same thing in like a couple of cents, essentially, and we're like all good with it. So the point I'm trying to get at is that money is great, but sometimes, when you don't have enough, you try to get the same thing done with more efficiency. And I think that has been a helpful learning.
Okay, so you've just been smarter, and maybe if you had more money, then like you wouldn't have thought of this new way. Yeah. Right. Okay. Anyone else?
I guess I could say a little bit.
Okay.
Yeah, recently with some of the ideas brought out earlier. So for us, it's a project. We have our specific goals to deliver something. If we have really unlimited resources, it's really nice to be able to build a thing that could be used in other astronomical projects in the future. And the same idea that was brought up before, like, so the next observatory doesn't have to reinvent some wheel, like hopefully our tool that's more generic, not just for our use case. Our team is trying to do that, but of course it's always limited resources ever. And also another thing is when the new technology comes up, the new tools are available, new kind of architecture that's become available. Some assumptions in the old days might just be false. And then how do we re-architect to use the new technologies and refactors our software to be able to use the new tools? I think that's really nice. That's something really nice that I would wish we could do more if we have more resources.
So you want to build like improve the infrastructure, really, so the next observatory doesn't have to, like, you're building the next observatory already, right? With the present one. Is that kind of the...
Yeah, maybe that's a kind of idea I was thinking, like some tools that's more generic and more useful for different projects, and even beyond just astronomical projects. That
right.
Would be cooler.
Okay. Interesting. All right. Anyone else want to take a stab at this?
I mean, I think that if I had infinite money, I would probably actually not be doing anything super different from what we're doing right now. Like, I think that I think I would try to build out a network of people that were sort of adjacent to universities and research centers and whatnot, that focused on infrastructure and development and the open source space, but that were not themselves like employed at those universities, but were employed by some, you know, the extra university organization, whether it be like a nonprofit or a company or something like that. Because I think there's a lot of value in having like a sort of network of people that can connect at the level of open source projects, which are sort of inherently multi-institutional projects, but they can be like deployed to support the people in a specific institution, which have, you know, more specific institutional needs. I think that one of the challenges of open source historically is that like the people doing the work on the open source side are also inside of institutions, and institutions, they, in many ways, they have like an inherent incentive not to collaborate to the outside world, because universities like fundamentally care about things like intellectual ownership and claiming credit for things and stuff like that. And so I think that like decoupling the development side of things from the like, I want to put a flag in something and claim this is my project side of things would be a useful thing that money could try and solve that problem to some degree. And then I'd also probably set up like a lobbying wing that would go out into tech companies everywhere and try to convince them to adopt like community standards rather than building their own stacks and products for things, because I think that's another major sort of anti-pattern we want to move away from, is a future in which there are like 3 different cloud computing stacks. There's like the Google Cloud stack and the AWS stack and the Microsoft Azure stack, you know, and a bunch of like other smaller cloud specific stacks. I think that like there's this weird push and pull where in some sense that's what cloud companies would love, because companies want to build verticals that make it hard for people to like move between different products. And I think that this vision for cloud infrastructure that's like really beneficial to science, it only works if a lot of the tools that we use are effectively commodities, so that we can like immediately switch from one cloud provider to another, like at the drop of a hat. I think that finding ways to create that fluidity is going to be a really important part of making sure that we don't, you know, get locked into a bunch of different cloud vendor technology. And so I would probably use that money to try and set up like decision-making bodies and standards bodies, much like we have with the internet and other pieces of the infrastructure we rely on.
So yeah, that's so like, let me try and understand. So like if AWS and Azure and Google Cloud were all like had compatible APIs, then they would have to compete in a different way, but like science would be enabled, you wouldn't be locked in somewhere, right?
I mean, in some ways, a good example of this is Kubernetes. So, you know, 4 years ago, 5 years ago, whenever it was, Google open sourced Kubernetes, which was this way of sort of in a more hardware actual implementation agnostic fashion, you can like configure and provision cloud infrastructure. And what Kubernetes allowed people to do is basically use the same framework to deploy cloud infrastructure across a variety of different cloud providers. And it took a while, but you know, now we're at the point where each major cloud provider has their own Kubernetes offering. But you can also run Kubernetes on like OpenStack, you know, like Jetstream, the like US-based science research infrastructure, they're prototyping, deploying their own Kubernetes instances. And it means that there's really minimal effort in switching from one to the other relative to what it would have been like 10 years ago, right? You need to like relearn a whole new set of proprietary cloud-specific APIs and machine type, like all that kind of stuff. And so I think that, you know, again, it kind of gets back to that earlier point of abstraction, right? If you think of the internet as, or if you think of infrastructure as code, which is kind of the promise of cloud infrastructure, it's the ability to just like with a 3-line script say, hey, Google Cloud, give me like 100 nodes, each of which has 80 gigabytes, use it for 15 minutes, and then destroy the whole thing. And then in 15 minutes, give me another cluster of this many nodes, you know, like that kind of fluidity. So if infrastructure as code is the future, then like what are the abstractions that allow us to, with a human readable interface, control lots of different kinds of infrastructure that's out there? And I think that those abstractions are going to be what allows us to have fluidity across the different cloud providers. Kubernetes is like one example of that. It is itself, you could argue, not the most human-friendly abstraction in the world. That's like a whole other conversation. But I think things like that are really, really important. And the other part of it is just standards. So things like, in my mind, when people often ask me, like, what is the biggest impact of the Jupyter project? My answer is, at least right now, I think that the biggest impact is the existence of a .ipynb format. because just getting everybody to agree that like this is a notebook, it has this structure, it's like a JSON structure, you can like it or dislike it, but like, 10 years from now, every notebook-based user interface will be able to read in IPyNB. And that's a super, super non-trivial thing to accomplish, just to get everybody to agree on the same thing, right? I mean, you can imagine like what was it, like 8 years ago, and Microsoft introduced like a docx format and like broke all the old doc formats, and everyone's trying to figure out how to read in the new thing into their own interfaces. And like, that's the kind of thing that happens when you don't have standards bodies that say like, we're all going to agree on this structure, we're all going to build compatibility layers with that structure. And I think that's the kind of thing that is really like thankless, not sexy work, but it's really, really important in making sure that all the things that we build can like build on top of each other instead of competing with each other.
Yeah, I know. Well, that's one reason why the FITS file format has been so successful, is that, for astronomical images, that everyone agreed that, okay, that's what the image is going to be. And like it's stuck around. So it's popular, it's successful, it's like it might not be what we want in the future, but like it's definitely a good example of what you're talking about, of like a standard was created and people followed it, and that allowed for a lot of science. So yeah. Okay, does anyone else want to imagine their bright future? Tell us what it looks like. No, everyone's happy with their current situation. That's nice. Okay, let's see. I have just one last question that I have anyway. So what is 10 years from now? What are you doing with cloud computing? What's everyone else doing? So just, what do you think? Is everyone a cloud native? Is Python still around? Have we all moved on to Julia or something else?
I can give a shot, and it's actually just building on Chris's answer. He was mentioning about how the evolution has primarily been that all the changes and improvements are happening behind the scenes, and the user doesn't really need to or get to know all the changes. So same for cloud. I mean, the capacity, the acceleration, the compute is all increasing. From the user's point of view, how the magic happens behind the scenes is getting even more abstracted, and they are getting to the answer much faster. In a very similar way, like we are going to the world of a lot of no-code tools, where how when Apple builds its iOS, it's primarily builds with the least amount of sliders to move or configurations to change so that things just work. So for users who are new, the abstraction just becomes easier to join something new, to get their feet wet, to try out things out, till they start getting to like a higher, deeper level that they can start working in a particular area. But behind the scenes, I'm looking at this project called Runway ML. It's basically AI for artists. And what it does is it takes all the state-of-art models that are published on GitHub by researchers, and then it gives to artists with this abstraction that move your mouse, make some changes here, or maybe add a JavaScript link to another application here. And if you get a video of a person dancing, it does things behind the scenes to create these new effects, segment them, or do whatever, right? And do them fast. Behind the scenes, they have linked it to cloud with GPU containers to do that processing. All you need to know is where to put your credit card in. That's all. So that's the power of when magic happens without you knowing it. I think that will just happen more and more.
Okay, so like cloud computing and the services that it provides just become a commodity that that people plug into. Like, I mean, everyone has, like, most people have a cell phone, right? Like, they have a computer in their pocket, which, you know, was unimaginable like 30 years ago, right? And so your idea is 10 years from now, like, people will just use cloud-based tools just as, like, without thinking about them.
Somehow, you know, whether it's on your pocket phone or whether it's behind the scenes, cloud obviously takes a large portion of the compute for bigger things, but things work seamlessly. By the way, I'm just noticing that a lot of companies who do work in open source, then they want to make a name. So they have like a really well-used open source package. For example, Hugging Face, it's a really famous tool, a company in the like natural language processing area. When you have text, you use usually one of the tools from their team. And now it's like, how are you making money? And they say, oh, you know, you can host your models on our service by paying like, you know, X amount of dollars per month. And like, that makes sense. I do not know anything about cloud. I don't know anything about hosting a model. You take care of this, and I'll just gonna use your API, which I trained on my data set. So the tools are free. The infrastructure is where you make your markup. I think that's where a lot of the business side and open source can continue together, where we still get, you know, food to feed our families.
Okay. Thank you. Yeah.
Yeah, by the way, I think since last week or 2 weeks ago, Hugging Face is cash flow positive.
Ooh, that's good.
And they only have 30 employees.
Oh, really?
Yeah, it's amazing.
Same case with the OpenAI, in the sense, not that they're cash flow positive, but they do all this crazy research. They will generate sentences, train all these models, and then you turn that into an API and make money out of it. So things are getting easier.
Well,
okay.
I can answer your last question, Jack, too. In 10 years, I hope that in 10 years, the TRL of all these compute accelerators, all these technologies, and with the whole stack running on them, has been elevated to 7, 8, or 9, and it's just completely commonplace. You don't have to think about it, and that anything can have a Linux box that has this full stack on it. So you can do all these cool things and really do edge computing and make your sensors, your missions, telescopes extremely capable. But even so, even though you're able to run these powerful processes up there, you're still power limited. You still have to be very careful about how much power you use, just because of the solar panels you have. So that still forces you to make whatever machine learning models that you might use for inference or any data processing to be extremely power efficient. So I hope that by having those platforms be almost ubiquitous, but you're still power limited, that allows us to do a lot of cool things, but do a lot of cool things in an efficient way. And a couple of years ago, I went to a meeting in Geneva, and Anousheh Ansari was advocating for above the cloud computing. So that I hope that's the future.
Okay. Above the cloud computing? You just mean solar panels up there? Did I miss something?
No, you just do a lot of computing on your satellites.
Oh, I see, right. Okay. Yeah, some of the autonomy talks, like, it seems that future is very exciting, but there's a lot of work to do in that area. So there's a lot of really cool things we could do in space if we had the computing above the clouds. You're right. but yeah.
So we've got an hour now since the start of this Q&A and panel discussion.
Okay.
Would you like to wrap things up, Jack?
Well, I've taken a lot of notes from this session. It's been really great. I watched all the talks. Again, the wide range of effort is quite spectacular, and it's like I've been following this field for a while, and the bit is beginning to bear fruit, as far as I can tell. So, like cloud computing and the capabilities that it brings, I think, is beginning to mature for space sciences. So, I don't know, like it's just extremely cool stuff that everyone's doing. I wish I was doing more of it. So, but I guess, yeah, I guess that's my wrap up. So just like maybe whenever the next COSPAR meeting is, maybe when we do this again, I don't know, 3 years, 5 years, 10 years from now. How about 10 years from now? We'll see if we're computing above the clouds.
Yeah, that sounds good. And again, I would have loved if we had the chance to meet in person in Sydney. The picture in my background, that's where the meeting would have happened. I took this picture 2 years ago. But there might be other opportunities, and certainly there will be other COSPARs in person, hopefully with appropriate logistics. We don't have to depend on virtual solutions so much, or maybe the technology is so well that it doesn't really matter. I don't know. But I really enjoyed all the talks that were in this workshop as well as in the other 2 workshops, and I encourage you to look at the list of talks in the other 2 workshops, and you'll find some interesting things. For example, about rovers. There was a nice session about rovers. Lots of cool application on machine learning for space sciences. And then if you're registered for COSPAR, even if you couldn't find the talks during the actual COSPAR time because of the problems in the schedule, I think all the talks should be available from your iOS or Android app to watch until the end of the year. And there's a really good program there. I look forward to binge watching those talks at 2 times speed on YouTube. So thank you so much for your time. Thank you, Jack, and thank you to Monica, Barbara, and Miho Jandier for coming up with this program for the workshop, and all the great speakers and the audience. I hope there will be some new ideas and collaborations that might come up, and I might probably contact 2 or 3 of you about certain ideas I have. Keep safe, and wherever you are.
Thanks very much. Nice to talk to you all. Bye.
Thanks, everyone. Thank you, Mark.
Thank you.
Bye.